All right. Happy Monday. How's everybody doing? You all listening? Anyone doing this? Those things to travel. I ate way too much turkey and stuffing. I had a family in town, so I didn't have to travel. Perfect. Yeah, it's like if you most people, you don't have to travel. That's always good. Welcome back to campus. If you're on, we have only 3 more classes left before the end of the semester. We have today, we have Wednesday, and we have Monday. And then we have our final, which is 2 mini exams back to back, one covering our back, and then one covering the entire program, the entire semester. So we're going to do that. Take a look at the syllabus for the date and time. It's also listed on the part F page at the very bottom for the meeting exam. So take a look at those dates. I'm also going to send out an announcement with the details of the final, just so you have it in your inbox. It's also in the syllabus and it's on the part page. So take a look at all that. Well, welcome back to campus. I'm feeling great. It's always good to see you. We have a big question today we're going to try to answer. We're not going to answer it mathematically. We don't actually have a lot of math left to do. In part F, we're not going to deal with a lot of complicated math. We're going to do a lot of the work in part F using graphs. So we'll think about the model graphically. We're not going to do the solution using mathematics. Everything we do for the rest of the semester can be done using calculus. And if you want more information about these kinds of models, and you want to do them using the full rigor of what we do in economics, you can take a class which we cover a lot of intermediate microeconomics, which is the next in the sequence in microeconomics. So if you love this stuff, that's a great class for you. It's one of my favorite classes to teach. And there are lots of people who teach it in the econ department who are very good. Yeah, look at that if you're interested. So you'll remember on Wednesday, before break, we took mini exam E. And then directly after, we ran a bit of a simulation, right? I asked, were you my subject, Ryan? Yeah. So Ryan answered a couple of questions about his preferences for 2 different types of candies, which gave us what we called the indifference curve. All of the points where Ryan didn't care, the different combinations of candy he could have. So we had, it was like a mint candy and then a Hershey's Kisses. So we had these 2 kinds of candies, and Ryan was sort of trading with me between the 2 candies in a way that made him equally happy between a bunch of different combinations of the 2 candies. And then I sent you off to recitation to work with the budget constraint. And so you remember what we did in recitation with the budget constraint. So on one side, there's a thing called the budget constraint. And I'm sorry, the lights are out on the side. So this is what we call the budget constraint, which, so if you have 2 goods, we have apples on the horizontal axis and bananas on the vertical axis. If you have some level of income, some amount of money you can spend to buy yourself some fruit, you can divide our spending between these 2 goods. So I walk into Whole Foods and I think about how many apples I want to buy. Turns out if we break, this is a very large number of apples. I love apples personally. So we have income, which we can spend on apples. So if we spend everything on apples, we can buy y divided by the price of a, number of apples. So this is some quantity of apples given to us by how much we have divided by the price of the apples. So if we have $10 and each apple is $1, then we can buy 10 apples. $10, $1 per apple, we can buy 10 apples. If we spend everything on apples. So that's how we get the horizontal intercept for the budget constraint. This is how much we can spend if we spend everything on apples. Everything on apples. And the same is true if we spend everything on bananas. So this is income divided by the price of bananas. And we can spend, if we're thinking about two different goods, we can spend our money on either one. So we can price of apples times the number of apples we buy, plus the price of bananas times the number of bananas we buy. And we just need to make sure that we don't spend too much. It's like we can't exceed our budget. So we look at the two extremes, and this budget line, this is this is all linear. So the budget line connects these 2 points together. With what happens if we spend everything on bananas? What happens if we spend everything on apples? And then we have every possible combination of points in between these two things. If this reminds you of a production possibility frontier, your intuition is on the right track. This is the same 2 dimensions and the same idea, actually, as a production possibility frontier. PPF tells us what we can achieve. The budget constraint tells us what we can afford. So anything on the inside of the budget constraint is something we can afford. Anything on the inside or on the budget constraint, we can afford. Anything on the outside is unaffordable to us. We can't actually buy it using our level of income and the prices that are determined by the market. And remember, these prices are coming from the market for apples and the market for bananas. 2 different markets determine the price, and that tells us what we can afford. We also have this new thing, income, sitting here. Next class, we're going to talk about where income comes from. To do this requires talking about the labor market, which is one of our last topics. Okay, so we have a budget, which tells us everything that's affordable to us. We also, as you remember, we talked about the indifference curve. Ryan told me all of his, combinations of candies, like we just talked about. So the way this looked from last time looks something along these lines. And this isn't going to be an exact replica of the graph we did last time, but it will have the same shape. So on the horizontal axis, I'm just going to tell you my preferences for apples and bananas. I'm not going to sing the song. You know the apples and bananas song from kindergarten? No one? So I just grew up in a weird household. Well, this is awkward. Okay, so we have apples and bananas, and I like to eat both of them. What we're going to do is plot my preferences. Thanks to those who are laughing at my stupid jokes. We have like a week and a half left of this semester, and they're not going to get better. My preferences for apples and bananas look something along these lines. I actually have both apples and bananas sitting on my couch at the moment, because I bought both right before break. My preferences for apples and bananas look something like this. And we're going to call this the indifference curve 0. So I subscript to 0. This is the indifference curve for some level of happiness. So this is indifference. And this line represents all of the
points all of the combinations of apples and bananas where I'm equally happy. So just like we did with Ryan, we could ask, how many bananas would it require for me to be equally happy between 2 points? I have to give up some apples. How many bananas will make me equally happy? This is all points I like equally. Excuse the grammatical incompleteness. But so a way we can think about this, and I'm just going to sort of plot this. We can think about the idea of what the indifference curve is doing, similar to the questions we asked Ryan. We said, let's say we're at this particular point. Call this A1. At A1, we also have some level of bananas, B1. Now, if I'm going to give up some apples, so we go to A2, how many bananas will I have to get to be equally happy? So we go from A1 to A2. So I give up some apples. We go from B1 to B2. I must have more bananas. More bananas. So we have this fundamental idea about trade-offs. To be equally happy between these 2 points, to give up some apples, I have to get some bananas. This is the trade-off. This is what Ryan was telling us when he gave us his indifference. All these indifference points. In fact, this is actually how we constructed it. I gave Ryan some Hershey's Kisses in exchange for some of his mint candies. All right. So this is the part of the idea. But we can make this a little crisper. Do you remember on day 1, we talked about rankings? Preferences are just rankings, right? We said, I was introducing the class to you, talking about where we were going with everything. And we talked about rankings. It's like, you have 3 things, X, Y, and Z. And we said, let's say I like X more than Y, more than Z. We can turn rankings into numbers, right? We said we can just take these things and put them on a number line. And let's say I turned X, gave it a value of 10, gave Y a value of 5, and gave Z a value of 0. As soon as we can start working with math, which is exactly what we would need to do these economic models. We say we have preferences, which are just rankings. Preferences are rankings. But then we can turn the rankings themselves into numbers. This works very nicely when we have sort of a handful of things. But what if I walk into the store and I try to buy apples by the pound? So on the horizontal axis, I don't know, have you ever done this? You know, in a lot of places around campus, you can buy a single apple for a certain amount of money. But at some grocery stores, you can actually buy apples not by the unit, but by the pound. So let's say on the horizontal axis, we have apples by the pound. And then on the vertical axis, we have some measure of how nice these things are. This is what we call a utility. Utility. How many of you have heard of utility before? Faustin and Aiden and no one else. All right. So we have, which is fun. We haven't even talked about it in this class. We have utility, which is essentially just a way of representing our preferences. It's these numbers. I haven't called it utility, but fundamentally, this thing we introduced on day 1 is these numbers that correspond with preferences are just a way of representing utility. Turns out it doesn't matter what the numbers are, as long as they correspond to ranges. So we can say this is 100, we can say this is 50, we can say this is 0. These numbers give us the same rankings as these numbers. The number itself is meaningless, but what it tells us is a ranking. As long as the numbers give us the ranking, then it's a utility. Okay. Utilities are nice when we have a small number of things. But what happens when we have the entire number line, which is actually just an incredibly large number, a very large number of things? It could be any point on the real number line. Well, to do this, we can perform a similar operation where we assign each number of pounds of apples to a number, which gives us a utility associated with each point on the horizontal. This is what we call a utility function. Similar to those rankings, it's just we're going to do it over many kinds of things. Every number on the real number line. So on the vertical axis, we have utility. And I'm going to draw one example of a utility function. So could look like this. This is something similar to my utility function for apples. So as we increase the number of apples we have, we're better off. So on the vertical axis, we have higher levels of utility corresponding with more apples. So as I get more apples, I become happier. Or I like it better. Happiness is, we'll leave that to the philosophers. Okay, so let's say we go from 1 pound of apples, to 2 pounds of apples. We can find the utility associated with these two levels of apple quantities simply by taking these numbers and plugging them into the utility function. This is all going to come back to our indifference curve. We're going to answer a fundamental question by the end of class. Before we get there, let's just plot out this utility. So we have, at 1 pound of apples, we have a utility level. We plug in U of 1. So this is telling us the utility associated with 1 pound of apples. We can do the same thing with 2 pounds of apples. We take 2 pounds, plug it into our utility function, and this gives us utility associated with 2 pounds of apples. Okay, so this, we're going to talk about some of the details here and how it connects with indifference curves. But I just want to set up for you the fundamental question we're trying to answer today. Remember, we have this budget constraint, and we have this indifference curve. The indifference curve is fundamentally coming from this idea of utility, where we're ranking all of these things equally. But the question we're going to try to answer today is what we call the consumer's problem, which is essentially a math problem. Consumer's problem. Which is essentially asking where on the budget constraint should we live. There are a bunch of things that are affordable to us, but which one do we like the best? Which one of the points on this line do we like the best? If you're noticing a connection to utility, you're on the right track. We're going to bring these two ideas together. But let me just write out the question so you have it in mind as we work through the next couple of things. So, the consumer's problem is essentially asking the question where on the budget constraint should we live? Which, let me say this quickly, how much of A and B should we choose? We're going to formalize this, and we're going to talk about exactly how we solve this graphically. But to do that, we have to think about indifference and utility. Okay, any questions so far? Been rambling on and on. Okay, so this is how we think about preferences. It's just, rankings, and we can assign numbers, and then we have, like paths of things that can be represented on a real number line. We want a utility function. It tells us utility levels at a bunch of different points, a bunch of different sort of levels of quantities. Okay, so this is our utility. Let's talk about two different characteristics of utility before we talk about indifference. So first off, as I buy more apples, I like 1 pound of apples less than I like 2 pounds of apples. And we can see this because 2 pounds of apples has a higher utility level. How many of you like 2 pounds of apples more than 1? Okay, maybe a silly question. Probably everyone does. Why are you asking silly questions, Taylor? These are the questions I ask myself when I wake up. Okay, so we have 2 pounds of apples. We like it more than 1 pound of apples. So as we go from 1 to 2, maybe I'll reserve my questions for you to important things. We go from 1 pound of apples to 2 pounds of apples. We actually like it more, generally. Unless we're talking about, I don't know, trash in your trash bin. Like most things we like more than less. Okay, so we increase the quantity of apples, and we increase how much we like it. We go from 1 pound to 2 pounds. We like it more. So we have this increase in apples, in utility for apples, as we increase our quantity. And just like with costs, when we talk about marginal cost, we can talk about how much our costs have gone up when we increase by 1 unit. So we call this marginal cost. It's the cost of one additional thing. We can also talk about marginal benefits, which is the demand curve, right? Which is how much do we like the next thing. We talked about marginal revenue, which was the revenue of increasing our quantity by 1. So the revenue of one more thing. We can also talk about utilities in these terms, what we call marginal utility. Marginal utility. This is the marginal utility of 2. So I'm going to write a couple of definitions on the board. Part F is not definition heavy, but I just want you to see these things. So utility, this is higher numbers are more preferred. Marginal utility is the utility associated with 1 more. So this is the utility of 1 more. Okay, this is marginal utility. So the marginal utility of that second unit of apples, that second pound of apples, is the difference between utility 2 and utility 1. So just the difference between these two things. Okay, so this is marginal utility. We can also talk about utilities not just in 1 dimension, but actually in 2 dimensions. And to do this requires a bit of a picture. I'm not very good at drawing 3 axes on a graph. Well, let's draw it like this. So not only can we represent utility over 1 good, so we have utility over apples, but we can also write utilities over 2 goods. So utility of apples and bananas. So this is a function that takes in 2 values and spits out a third. One example of this could be a to the 1/2 plus b to the 1/2. The example of this could be a to the 1/2, which generally looks like the utility function we just drew. We're not going to do anything with this mathematics, but if you like this stuff, feel free to write it down. If this scares you, don't put it in your notes. You won't need it. When I grew up, we used to go to a state forest, and it had, anyone know Cowan's Gap State Forest, State Park? There was a ranger station, and this ranger station had this topographical map. It was like a map with different elevations corresponding to different mountains in the area. It was a three-dimensional graph, essentially, a three-dimensional map. One dimension was the height, which came out of the table. It was like on a table, and there were these heights were coming out of the table. We had two dimensions, which were the sort of horizontal spatial dimensions. Then we had a third dimension, which was height. This utility function is a very similar thing. You have two dimensions, sort of the latitude and longitude, the spatial dimensions. But then we also have height. So it's coming out of, this utility function is coming out of the whiteboard. Instead of drawing a third dimension in space, what we often do is draw a contour plot. So these lines, which represent equal elevation, like a topographical map. So, we can climb the mountain, and these each correspond with different levels of utility, different heights coming out of off the whiteboard. So this is, some utility level 1, utility level 2, utility level 3. And we can climb the mountain, sort of coming off of the whiteboard. Imagine a third dimension coming off the whiteboard. That's what this is doing for us. 3 dimensions, which is a little complicated to draw, but what we do is we talk about contours. All these possible combinations of apples and bananas where we're at the same height, which is an indifference curve. So behind the scenes for Ryan, when he was telling me about his preferences for candy, we were walking around the mountain. And what Ryan would like to do is try to get as high on this mountain as possible. Try to climb this mountain as directly as possible. So let's come back to Ryan's graph for a second, and we'll talk about one more characteristic. So I'm going to sort of summarize this picture on this graph. Every point on the indifference curve corresponding with U1, we like equally well. It's all of the possible combinations that were indifferent. When we jump to U2, we're saying we're actually happier at U2 than we are at U1. And just as an example, if I were to draw a vertical line, we can tell we like U2 better than U1 because on U2, we can have more bananas than we could on U1 at the same number of apples. So we definitely like U2 better. So this gives us a fundamental characteristic of indifference curves, which is that more is better. We want to climb the mountain, and we climb the mountain by moving further out. Okay, next. Any questions about this? I'm going to give you a couple of challenge questions. Okay, first challenge question. We have a blue point, which is here. And let's say we start at x0. Call this x1. Quick challenge question for you. Do we like x1 better or worse than x0? How many of you think we like x1 better? How many of you think we like x1 worse? Nice, very good. Your intuition is on the right track. x0 is equally preferred to everything on this line. And we can find that there's a point that x1 has more bananas then and the same number of atoms as some point like right around here. So we know we like x1 better than every point on I0, including like some point up here. Even though we have more bananas up here than we do down here, we still like x1 better because it's on a higher indifference curve. The same is true for x0. X0 has more bananas, but we like x1 better. And that's because we're compensating by giving more apples in exchange for fewer bananas. Okay, I have another challenge question for you. I'm going to draw an indifference map, so the xy plane, and then you're going to construct the indifference curve. And we're going to take about a minute to do this. This is a relatively challenging indifference curve. All right. So I want you to think about your preferences over right and left shoes. On the horizontal axis, we have left shoes. And on the vertical axis, we have right shoes. And now I want you to draw an indifference curve that runs through x0. So I want you to draw this on your sheet. Maybe check a couple of points around x0. Like what happens if you add one more right shoe and you don't change the number of left shoes? And then what happens if you add more left shoes without changing the number of right shoes? And then maybe what happens if you add more of both shoes? Do you like that more or less? Take about a minute here, check with your neighbor after about 30 seconds, and then we'll do it together on the board. Go. Yeah, so let's.
Technically, I feel like you can. Is no shoe better than one touch?
All right, how are we all doing with this silly question? It may seem like a silly question, but this is a real type of indifference curve we draw. Someone help me out here. What might this indifference curve look like? Oh. Like this. Yeah. There is a line that looks like that, that will be important. I'm gonna toss a candy. Someone else. Toss.
I drew a horizontal line.
Oh, horizontal line. Okay. Where does it start?
At the y-axis, and it just went straight to the center to XO, and that's it.
So just this.
Yeah.
Also toss a candy. But this is in the direction of on the right track. Yeah, right.
Is it? I'm just thinking sad. Is it kind of like that, the shape of that line right there?
Kind of curves a little bit.
Through X.
So maybe the curve that kind of looks like this.
Yeah.
Also, we're getting closer, but we're not quite there yet. Let me ask you an intermediate question. Let's look at x1. What I've done with x1 is I've increased the number of right shoes without changing the number of left shoes. If I were to just give you another left shoe, all of you are probably wearing shoes at the moment, I assume. If I were to give you another right shoe, how many of you would be happier because I gave you just the right shoe? How many of you would not take the shoe if I gave it to you? Okay, most people. I would not take just one unmatched shoe. I would say I'm equally happy between x1 and x0. Right? I'm equally happy between these 2 points. So I'm going to draw my indifference curve through these 2 points. It must go through these 2 points. In fact, it'll continue. If you give me 100 right shoes and no more left shoes, I won't take any of them. And the same must be true for left shoes. Nothing special about my left foot. It's like a quarter of a size larger. But nothing else is fundamentally interesting about it. So if I increase the number of left shoes without increasing the number of right shoes, it doesn't make me any happier, right? Okay, any questions about this? Can you see it now? Right.
What if you get like one the right shoe and a left shoe?
So if you get one more right shoe and one more left shoe, then that puts us at, let's say, an x2, and we're now on a higher indifference curve. So we have climbed the mountain. So that puts us up here. So just like a bunch of people in the front row mentioned to me as potential answer for this question, there is a line that runs through these things, but it's not the indifference curve. It just tells us sort of this optimal combination of the two. Okay, so these right shoes and left shoes are what we call perfect complements. We need both of them. So this is what we call a perfect complement. Just like you all are excellent students. Perfect compliment. Okay, that was a reasonable joke, I guess. We said, I need both. Okay, another challenge question for you. Use a similar approach for this question. On the vertical axis, I'm going to have pens. And on the horizontal axis, I'm going to have pencils. Take about a minute here. I want you to set up an indifference curve that runs through this point, x0. Think about the trade-offs here, and then plot a bunch of indifference points, and then draw a line through them. And then check it with your neighbor. Take about a minute. Mental telepathy is strongly discouraged. Verbal communication in any language you like is encouraged. ASL is great. We can't take forever on this because we have a big question to try to answer. Take me 3 seconds here. Get it? Okay, when I was in college, I took all of my exams in pen. And then when I entered grad school, I started taking all of my exams in pen as well. And as things became harder and harder, I needed to be able to erase. But most of the time, so like, I wrote my notes for today's class in pen. But if you were to swap a pen with a pencil in my backpack, I'd probably be generally about equally happy. Maybe not perfectly happy, but pretty close. So if you were to take one of my pens and swap it for one of your pencils, 1 to 1, I would be generally equally happy. There might be some curvature to this, but it will look something like this. Ryan's preferences for candy are slightly curved because Ryan, prefers some combination of both. And you might see that with pens and pencils. Like I might want just one pen, maybe most of the time I don't really care, but I want one pen just in case. And the same might be true for pencils. Like I do everything in pen, but then for exams, I bring my pencil. But generally, it's going to be something like this. This is what we call complements. Substitutes. These are our substitutes. We trade between I don't care. Most indifferent thing I read on the board. Okay, so this is an indifference curve. We essentially don't really care whether we have pens or pencils. Pretty close substitutes. So how does all of this relate to our fundamental question, which is, okay, we have this budding constraint. How do we pick a point on this budding constraint? Well, we have all this apparatus for constructing indifference, right? We have utility, which gives us preferences in 1 dimension. We can do preferences in 2 dimensions, which gives us a contour plot, which tells us about the shape of preferences, right? Like we have to give up some of A, we have to get some more of B. So we're giving up some utility in the A dimension to get some utility in the B dimension. So marginal utility, changes in utility give us this indifference curve. So we have this mountain we're trying to climb behind the scenes, contour plots, but we can't climb all the way up the mountain. Fundamentally, we can only climb on this area. I'm going to write down the framework for thinking about the solution to this problem, the consumer's problem. And you'll remember some of this notation from when we talked about the firm's problem, which was how does the firm maximize their profits? For the consumer, we have some utility function with 2 inputs. We have the utility of the A and B. We want to maximize this thing. We want to be as well off as possible. So this is our measure of how well off we are, right? We just rank some stuff and we pick the thing we like the best. So we're trying to pick the thing we like the best. So we bring max to say we're maximizing this thing, the highest point on our indifference curve that we get to. But we can't afford everything, right? Some things are just unaffordable to us. We can only afford what's on the inside of our budget constraint. So we can't just pick anything. We're actually going to be constrained by what's affordable to us. So we're going to write down the budget. So the present A times A plus the present B times B. So we want to be as well off as possible while being within our budget. While staying within our budget. So to do this, unfortunately the light's out. I wish the light would be on that last board here. I'm gonna ask you a series of questions, and you're gonna tell me which one is better
than the other.
Series of 3 or 4 questions. And when we finish this sequence of questions, we're going to have solved the constraint problem. There's a bunch of fancy mathematics. And if you want more about the actual mathematical solution to this, there are classes for you. What we're going to do in this class is just talk through the intuition. So I'm going to set up one point. We'll call this x0. I'm going to draw an indifference curve through x0. So we have the indifference curve which goes through both x0 and then also x1. So the question for you, do we like x1 or x2 better? Hands for x0. How many of you think we like x0 better than x1? How many of you think we like x1 better than x0? And how many of you think we like them equally? Very good. How many of you think x0 is affordable? How many of you think it's not affordable? It's affordable. It's on the budget constraint, so we can afford it. How many of you think x1 is affordable? It's on the budget constraint, so it's affordable. So x0 and x1 are both affordable, and we like them equally well. But let's say I were to switch from x1 to x2. We're going to go from x1 to x2. I'm going to draw an indifference curve through x2. This indifference curve 1. How many of you think we like x1 better than x2? How many of you think we like x2 better than x1? Hands up is correct. We like x2 better than x1 because it's higher on the number. More is better. So we're going to continue, and x2 is on the budget constraint, so it's affordable. So we can continue to climb the mountain until we can't move further in and increase our indifference curve. There's one point where we cannot climb the mountain any further without things becoming unaffordable. And that happens right here. At the point of tangency between these two things. The point of tangency between the indifference curve and the budget constraint. I'm sorry to hold you over. I'll see you all on Wednesday. Have a nice week. Welcome back. Yeah, you too.